All right. So, greetings. Welcome to week six. Oh, sorry, week seven. So, in previous interactive session, we went through the root locus, and the this week on the NPTEL corresponds to the root locus again, but with the positive feedback. So, what we have decided is that today we'll go through some MATLAB and Simulink examples, and we will connect to what we have done in our previous discussions. So, uh, welcome. So, here in week 5, we went through one question where we have a control system and we should ensure the closed loop stability and satisfy some performance criteria. So, we had been given this second order transfer function y double dot of t plus 4 into y of t equals to u of t, and we were asked to figure out which among these controllers, that is PID, PI and PD, stabilize this system. What is the range of controller parameters uh, of the chosen controller that would ensure the closed loop stability? And this is all about the stability. The second question is more about performance criteria. So once we have figured out a controller which can stabilize the system, we want the closed loop system to have some desired performance. So we wanted settling time below 1 second and to have maximum peak overshoot below 15%. And for this, we had asked to report the damping ratio of and the real part of the poles. So in this particular case, we tried various transfer functions, various controllers, and we arrived at some conclusions. Today, we will quickly take a look at MATLAB example uh, corresponding to the same question, so that we can connect from what we have been doing in the classroom and in our assignments to how it should be done in MATLAB. So we'll go through following things. First, I will tell you what an array is. It's a collection of elements. What a matrix is. How do we realize these things in MATLAB? Then we will go through what a transfer function is, how the transfer function is written in MATLAB, and how to realize its step response, how do we simulate the linear system, and how do we have this root locus. Then we will go to the Simulink part and we'll quickly discuss Simulink environment, look at what sources and sinks mean, and then coming to our own context of control systems, we'll see how to realize the transfer function block, what is the PID block, what all options we have, and how can we tune the PID controller. Here we will corroborate our findings from week 5, and then we will move on and uh, tune the controller in the way we want. So let's start with MATLAB. All right, so okay, so this is the MATLAB environment. Here we have .m files which we can where we can write the code, and this is the command window where we can try out smaller blocks of code or say single commands. Here is the workspace where we can visualize various elements, and we can, so let's see. Uh, so let's call a as 1. So this is a scalar, and it will Shravan, is the font size okay, or I need to increase it?
You can slightly increase it a little bit, but it is fuzzy.
Okay, All right, let me quickly do that. Hmm. Okay, I think this is this better?
Yeah, it's
Yeah, it's
clearer.
clearer.
All right, great, thanks. So let's. All right, so this is a scalar. Its value is 1 here, and if we have to type an array, let's have it this way: 1, 2, 3. So we'll have an array with three elements: 1, 2, and 3. Okay, if we want to write a vector, then we write it as then we can write it as 1, 2, and 3 transpose, so that it comes like a vector. Or another way to write the same vector is this way. So when we use comma, that means we are moving on to the next element, and when we use this semicolon, that means we are going in the next row. So this is how to write an array. This way we can write comments here. So if we have double tabs, we can write as comments using, we can create sections using double uh, percentage symbol and single percentage symbol for normal comments. So how to write an array? An array would be, say, 1, 2, 3, which is kind of a row. If we want to write a vector, we can write it as 1, 2, and 3. So if we run this, we will get what we have written: array as a here and vector as v. So same things we have written. We can use command clc to clear the command window. Then uh, a way to write matrix is the same way as we wrote array. So let's have 1, 2, 3. Then in next row we'll have 4, 5, 6, and in next row we'll have 7, 8, and 9. So if we run this, we can see our matrix A. Another, there are some special matrices like an identity matrix, which can be written using command I, and if you give it uh, a number, it will just create the identity matrix of dimension whatever you are given in, for example 3. So this way we can write a matrix. Now coming to matrix operations, we can multiply a matrix with a vector to get another vector. So let's run this. Here the matrix A was multiplied with the vector V to obtain vector V1, which is 14, 32, and 50 in this case. So and we can multiply different matrices, like say A into A as A square. I'm writing here as A2, right? So this way we can have matrix operations as well. Now we'll come to discussion on control systems. So we have seen transfer functions. So the way to write transfer function is using command tf. Okay, so there we can have a numerator polynomial and a denominator polynomial. So let us consider uh, a first order transfer function with constant with its gain term as 0.9, and if we run this, this is what the transfer function is coming out. G of s equals to 0.9 over 0.26 s plus 1. So it is a continuous time transfer function. So we can give different inputs to the transfer function. For example, say step response. So we have been giving unit step input to the transfer function. The command for realizing this is called step. So if we give step g of s and run this function, it will generate the step response. Okay, so this is the generated step response. Here, let me make it look better. All right, so here is the amplitude. We gave it a step input, and it is taking uh, it's behaving like a first order response where it's slowly going up and reaching the uh, steady state gain that was 0.9. So if we take a data point and look approximately where we get 0.63, so all right, so the 63% of the amplitude, which is 0.9, so approximately, let's use this calculator here, 0.63 into 0.9, that is 576. So let us see where this 576 comes, the amplitude, and it will come around the time constant which we had given, which was 0.26. So this is the so the time constant for the first order system, tau, is essentially the time at which we reach the 0.63% of the, or sorry, the 0.63 times the steady state output of the transfer function. Let us write another transfer function, say this time a second order transfer function.
Pawan,
Yes,
is there a shortcut to get all the performance specifications or do we have to do it manually?
all the performance specifications I need to check once, but there are like advanced tools when we go to systems like app and PID tuner. It tells you multiple attributes in
Okay.
together. So for now, let's understand things one by one.
Yeah.
Okay, yeah. So 1, 5, and 6. So let us try this second order transfer function. All right. So since this is a second order transfer function, let us try to take a look at poles of this. I think we can find it using the command pole. So let's run it. And right, so these are the poles, -3 and -2. So if the poles are negative, then the system is said to be the stable system. And if I add an artificial zero here, all right, let us include a zero at say 0.9, and then we can use command 0 to obtain the zeros of the transfer function. So here you can see, right, answer pole is coming here and 0 is coming here. So let's call this as PGS, and let's call this as ZGS for the zeros. So this command can help us find the zeros. All right. So let's take a look at step response of say this second order transfer function as we saw for the first order. So that can be given by command step GS1. Okay, and let's run this. This is the step response of the system. Here we can figure out the maximum peak, which is somewhere around here. Its amplitude is 0.2, and the time it is taking is 0.622 seconds. And the steady state value for this transfer function is uh, this 0.15. All right, so this is how we can obtain the unit step response. Now let's look at, we have given the step input. Let's try some other kind of inputs. So let's try simulation of a linear system with some given input. So here we have the transfer function G1s, and let us get some input, which is say 1 plus 2 sine. uh, so let's start from 0 to say 10 seconds in steps of 0.001. So let's see if this works out. All right, so we can just visualize the input using the command plot. So this is the input we are giving. It's a sinusoidal wave starting from 1, and it's oscillating about it with the amplitude of 2. So the time vector for this is given by t, which we can copy directly here, and if we run this, all right. So let's plot a figure using the plot command, where I can give t and u, and I can label the axis using the command called xlabel, where the time is given in seconds, and output is given, sorry, the input is given here. So it generates a plot with the labels you have given. Now for simulation, the command we have is called lsim. So if we need help regarding any command, we can uh, look it up in the command window by typing lsim. What does it say? It requires us to give system, input, and the time. So system is g1 of s, sorry, gs1, input is u, and time is t. So if we clear this, so using the lsim command, we can simulate any linear system for any input for the given time. So let's plot our output as well. Let's plot it in the same plot. Here we are using the command called hold on, plot t and y. So the blue plot is the input which we have given, which is a sinusoidal wave oscillating about 1 with an amplitude of uh, 2. So the peak to peak is 4, that is from -1 to 3. Alright, so this is the way in which we can simulate different inputs in MATLAB. If we were to give it some random noise, let's use Gaussian random noise with, say, with the standard deviation of 0.01, and let's give this random number a dimension to work with. So this should be size of the time which we are working with. So we can see that the blue one is where we have added lots of noise, and the red plot, which is the output of this system. Alright, so this is one way in which we can introduce noise and then test our controllers for uh, so the yeah, that is the way in which we can demonstrate we can introduce some noise in the input. This would be useful to figure out the disturbance rejection capabilities of the controller. So now, uh, I think with some understanding on MATLAB code, let's move on to the portion on Simulink. So we can open Simulink from the home button using the Simulink button. So it will open a starting page where it's loading templates, and we can pick one of the template. Let's create a blank model. So Simulink models or the Simulink environment allows us to have a graphical interface where we can have various blocks called Simulink blocks, which allows us to develop very complex systems. So, all right. So once it opens, we'll get started with the Simulink portion. So in the Simulink portion, first I will show some of the elements of Simulink environment. Then we will look at what the sources and sinks mean. Then we will look at the transfer function and how do we realize the transfer functions in Simulink. Then we will see the PID controller block. So, so this is how the just one second. This is how Simulink looks. It has various tabs. First is for simulation. Here we can browse the we can open block library where various blocks are shown, and here this is where we give the simulation time, how to like run command and stop command. In debug, it allows us to uh, diagnose and figure out how well our Simulink models are performing. Then in modeling, we have some advanced features, and in the apps we have different apps which allows us to work with external systems as well. It's like embedded C coders, robot operating system, and so on. Today we'll just look at some basic blocks. So if we click on the library browser, it so this is the Simulink library browser. Here we can see blocks coming from various toolboxes which are available. And first we'll just look at Simulink library and the sources block and the sinks block. So in the sources block, we can have different sources like uh, say a step input, a sine wave input, uh, and of course some kind of random noise like uniform random number. We can of course generate some waveforms. So as we have been working in our course on control systems, we have been looking at step response extensively. And in upcoming weeks, we'll be looking at frequency response, where sine waves will also come into picture. So let us start with a step block. We can just take it and drop it here. So this would allow us to give some kind of a step input. Now let's come to the sync aspect. Uh, these are the display and scope, which are predominantly used. Along with that, we have sim out, that is, it will send the data out in the workspace in MATLAB so that you can work on it after you run the Simulink model, or you can write it to some file. So let us also bring in uh, a scope, and we can just connect the inputs and outputs to join to visualize the output of the block. So in the step block, we have to give the time at which the step input is given, initial value, and the final value, and sample time. When we give sample time, it will select the sample time which you as a user would be providing. So if we go to this settings block and open this configuration parameters, we have different kind of solvers available. We'll keep the solver selection automatic, but we will fix the time step to 0.001, that is 1 millisecond. So if I run this, it will generate the step response in the scope like this, right? As we gave the input at time t equals to 1, we are going from 0 to 1. Now we can also type in here to get blocks. So let's bring in a block for transfer function. Here we can give the numerator coefficient and the denominator coefficient to complete the transfer function description. So let us look at the transfer function given in this particular problem. This is week 5's notes. So the transfer function for the plant is P of s, that is 1 over s square plus 4. The poles of this transfer function were plus minus 2, that is, they are complex poles on imaginary axis. So numerator is 1 and denominator is 1 and 4. So if we press enter, uh, so we have 1, 0 and 4, because it is s square plus 4. So we can see that here. And if we snap it in place, this is the transfer function we have. When we now simulate a step input and click run, this is how it responds. So it is giving a sinusoidal response because its poles are on the imaginary axis. That means it will generate some sinusoidal response. So uh, but we wanted to follow the step response, so let us create a closed loop system. So to create a closed loop system, we can use the PID controller block. So this is the PID controller block. Now if we remember the block diagrams which we have been drawing, we use we feed in the error, that is, if this is the reference and if this is the controller, then we feed in the error to the controller. So if we use the subtract block, take in our reference as the input and then take in the feedback. So we are taking feedback directly because it's unity feedback, so nothing gets multiplied, and there is no yeah, since it is unity feedback, we can directly take it, and since it's negative feedback, we are subtracting. So this signal is the error signal which goes into the PID controller. Now let us look at what we have understood in this particular example. When we looked at the poles, they were also on the imaginary axis, and we realized that the proportional controller cannot stabilize the system. So let us pick Kp as 1 and go ahead and check with Simulink for ourselves. So my integral is 0 and derivative is 0. It is essentially a proportional controller with P as 1. So let's see if the feedback can help us improve anything. Its response was almost similar, but the amplitude has shrunken a little bit. So the maximum value previously it was 0.5, now it is 0.4. However, we are very far from what we desire. So let us see what we did for the integral controller. Here also we realized that the denominator polynomial of the closed loop transfer function uh, is not Hurwitz, that is, it does not have all of its poles in the left half of the complex plane. So this I controller should also produce a response in which, let's select 1 as a value. So the I controller also should not be able to stabilize the system, and here also we can see that it is oscillating and moving up, but its response is not what we have desired. Then we will take a look at the derivative controller, where if we just use derivative controller, that is C of s is equals to kd into s, mm, so this derivative controller can stabilize the plant if kd is chosen to be positive. So let us see how the simulation comes up using just the derivative controller. So it does not even allow us to have a derivative controller because generally it's advised not to use uh, derivative controller in isolation. So here we have also included a filter which is like this. So in MATLAB, the derivative controller is given like, where d is written, you can read it as kd into n over 1 plus n into 1 over s. So this filter coefficient allows us to get rid of high frequency noise. So we said that it can theoretically stabilize. Let us see. So although the system's input is has died down, it's not 1. We wanted the reference value was given from 0 to 1. However, the response dies down to 0. So this is again is not what we desired. So let me improve the scope and let me put a scope with 2 entities. So if we click on scope here and type number of ports to be 2, it will generate scope with 2 ports. So let us use this as r of s, or say, okay, all right, let's write it as reference and output. So now we can visualize things together. As what we wanted, given here in yellow, that is the reference, and the output here is given in blue. Although theoretically it is able to satisfy the condition for stability, the performance is something which we are very far away from. Then we looked at a PI controller where in the routes array we encountered this 0, and that's why this PI controller could not stabilize the uh, control system. Finally, we looked at the PD controller where the closed loop transfer function is given by this, and it's uh, if the first row is all positive, then if the first row in the routes array is all positive, then we can say that the system would be stable. That means KD should be greater than 0 and KP should be greater than 4. So this is where we drew the controller parameter space. So what we can check is if we violate any of this condition given here, that is not picking a point which is not in this stable denoted zone, then we should not be able to have a stable response. So once we'll check that, and then we'll pick few points in it. So a PD controller where derivative is less than 0, say if that happens, and right, so KD, if I violate this condition but I ensure this condition, say 2, then let us see what happens. As per our analysis, we should get a unstable response. All right, so we can see that the output is just blowing up. Now if we ensure the derivative is stable, but we have this as -6, the proportional value, then let us examine what happens. This time we are violating the Kp greater than -4 condition, but we are respecting d Kd greater than 0 condition. So we can see that it's going in negative towards very high values. So again, which is an unstable response. So if we uh, put 5 here, that means we are satisfying both the conditions for stability. And in such a situation, our output should kind of stabilize. So here we have it is responding to the step input, but again we have lots of tuning to go for. But we are not looking at any behavior like output dying to 0, or it's going towards infinity, or unsustained oscillations. All right, so uh, let us try to tune the PD controller, and I'll just make it into half screen. So let us make this proportional constant as higher value, and derivative, so we'll increase derivative as well. We are looking at some steady state, seemingly steady state bias here. So we have made our response smoother by increasing the derivative, and it has also gone closer to the derivative controller. Now, if we include some integral component and make it a PID controller, the integration PID, when we include integral controller part, it ensures that we get zero steady state error. So once the system settles down, it will go, and as we can see, it's approaching towards 1 in this. Since our simulation is ending, we are not able to see that. So let us improve our gains again. Say let's increase proportional gain, and see if we are able to close in faster. And we'll also increase the integral gain so that we reach the zero steady state faster, and derivative to smoothen our response. So our response has smoothened up. So if we need more smooth response, we can increase the derivative even more. And let us try with this. So we have uh, improved that. Now we can take this closer to the yellow line by changing the integral gain. So by increasing this, we should be able to reach steady state faster. Okay, it's better. Let's take it to 20. So we are reaching the steady state much earlier now. Right, much better. So a general notion for PID tuning, which there are certain rules like Ziegler-Nicholas and all. Sometimes a hands-on quick view point is that you keep increasing the proportional controller gain, and then improve change the derivative gain so that you respond smoother, and change the integral gain so that you can quickly reach the steady state value. So that is what I have intuitively demonstrated here in the PID tuning section by hand. Of course, there are tools like PID tuner here. So if we double click this, it allows us to do tuning. But it does lots of processes which you as a control engineer should be able to understand, then relying on these kind of tools. So, so do we have any questions? That's all I wanted to discuss today.
No, it's all clear.
Sorry.
It's all clear. It's all clear.
All right. Great. So thank you for joining. I think we can close today's session.
Thank you.
Thank you.